Alright, one last example of a surface integral of a scalar function. We want to integrate xz over a piece of the sphere of radius 3 centered at the origin. And let's look at what piece that is. So we have x, y, and z. We have a sphere of radius 3 centered at the origin. And then this is a little bit weird. This is not the piece we normally look at. We have x less than or equal to 0. So we've got to be to the left of the yz plane. Y greater than or equal to 0, z greater than or equal to 0. So we actually have like this back octant there. That piece of the sphere. Okay. Sphere, we should probably parameterize with something that looks like spherical coordinates. Okay, so R, and then the rho in spherical coordinates is fixed. So we'll keep that as 3. Let's see if we can remember how spherical coordinates work. The phi made an angle with the z-axis, so the z portion should be 3 cosine phi, which means the x and y portions should have sine phi in them. And then x also has a cosine theta, y also has a sine theta. Okay, so R is now parameterized by phi and theta, where rho is fixed at 3. Okay, so this is a little bit ugly now. R sub phi is then 3 cosine phi cosine theta, 3 cosine phi sine theta, comma, negative 3 sine phi, and then R theta is negative 3 sine phi sine theta, comma, 3 sine phi cosine theta, comma, 0. Okay, now I have to calculate a cross product, so that's slightly annoying. It's okay. Let's just make sure we do that. 3, a little bit of writing here. 3 cosine phi sine theta, negative 3 sine phi, and then negative 3 sine phi sine theta, 3 sine phi cosine theta, 0, right? Okay. Let's see what this is. This is 0 minus a negative. So positive 9 sine squared phi cosine theta, comma. And there's this plus minus plus here. So that's a minus, and then the 0, minus, 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 minus. So for a total of positive, actually, in the y-coordinate, 9 sine squared phi sine theta. Okay, that's good. And then in the k, it's 9, let's see, 9 sine phi cosine squared theta, minus a negative, so plus 9 sine phi cosine sine squared theta. And then we can factor out this first part, and we're left with a sine squared theta plus cosine squared theta, which is 1. So the z-coordinate actually ends up being 9 sine phi cosine phi. There. Okay, now we gotta find the magnitude of this. That's rough. Okay, r phi cross r theta. Let's see. So, any easier ways to do this? Well, we have that part. So, we're going to get an 81. Let's see. Well, maybe we'll take out a 9. So then we won't worry about the 9, right? We can take out a 9 from all of these and not worry about that. Okay. Then we're going to get a sine to the 4th phi from squaring those. But then that'll contribute a cosine squared theta and a sine squared theta added together. So that's 1. So that's taking care of the squares of the x and y coordinates. And then we're going to have a plus. 9 has been taken out, and then the z-coordinate contributes a sine squared phi, cosine squared phi. Okay, and that's great. We can factor out a sine squared phi, and then we get a sine squared phi plus cosine squared phi is 1. So this is 9 root sine squared phi. And phi goes between 0 and pi, so sine phi is always positive, so we don't have to worry about weirdness in taking out of the square root. Or sine phi is always non-negative, is what I should say. So, calculate all that, you should get a magnitude of 9 sine phi. Okay, now what did we want to integrate? We wanted to integrate xz. So we got to take all of this x times this z, and then we're going to integrate, make sure we put a 9 sine phi there, and then figure out the correct bounds. Okay, fun. We got a 3 from the x and a 3 from the z and a 9 from here, so it should be a total of 81. And then x had a sine phi, and we get a sine phi here, so that's sine squared phi. X also had a cosine theta, z also had a cosine phi. So should be this function integrated with respect to phi and theta. Okay, and then let's think about the region. What happens? So we want this portion of the sphere. This is theta going from pi over 2 to pi. And then once we cut that off, we know that phi starts at 0 here and goes down to pi over 2. Okay, so phi goes from 0 to pi over 2. Theta goes from pi over 2 to pi. Okay, then we just need to calculate this integral. We can do a quick u substitution. U equals sine phi. Then du is cosine phi d phi. So then pi over 2 to pi. We're going as phi goes from 0 to pi over 2. This is 81 u squared. Cosine theta is a constant, basically d u d theta. Okay, and then that integral works out nicely. 81 is divisible by 3. So that's good. So we get 27 u cubed cosine theta. Phi goes from 0 to pi over 2 d theta. Sub back in, u was sine phi. So 27 sine cubed phi cosine theta 0 to pi over 2 for phi d theta. And then sine of pi over 2 is 1, sine of 0 is 0. So integral pi over 2 to pi, 27 cosine theta is all that's left, d theta. We want then 27 sine theta going from pi over 2 to pi. Sine pi is 0 minus sine pi over 2 is 1, so minus 27. Okay, we got a negative integral. Is that okay? Sometimes we feel like integral means area or volume. So let's go back and check. We wanted to integrate xz over this region where x was less than 0 and z was greater than 0. So that's good. Yeah, we definitely expect that to be negative. Xz is negative at every point in that region. So that's perfect.